Okay, buddy, let's try out some problems dealing with oblique shocks. So let's see here. I've got an oblique shock wave, okay, right there, with a wave angle of 30 degrees in a Mach 5 flow. That looks good to me. I like it. And I'm going to try to draw it more accurately because if it was oblique shock wave, it would have some sort of thing deflecting out of the way. It says it has a wave angle, so that is beta equal to 30 degrees, and this is a Mach 5 flow. Almost said 5 degrees. Between pressure and temperature are the following. So pressure is going to be equal to 2.65 times 10 to the 4th pascals. And the temperature is going to be equal to 223.3 Kelvin. As a note, that corresponds to a standard altitude of 10,000 meters. Fun! So what do we want to know? Pretty much everything after the shock. Okay, so I want to know P2, T2. I want to know M2. I want to know total pressure and total temperature. So P02 and T02. A lot of stuff. How are we going to do this? Same way we always do it. We go to the tables. Seriously, we're going to go to the tables a whole lot for this. But we can't go to the tables to start, because remember, when it comes to oblique shocks, we do not want the Mach number, we want the normal Mach number, the Mach number that is normal to that wave right there. And so I need to calculate that. It's not that hard, we see the equation a bunch. And so what it would be is M(n)(1), that's the normal Mach number, is equal to M1 sine of beta. Wondering why that is? I have this flow, it's coming in here. I can even draw it like this. Intersects, that angle right there is beta. This flow is going to have a normal component and a tangential component. This one right here is the normal component. This is M1. And so if that angle is beta, this angle is beta 2. Opposite over hypotenuse is sine, and there we have it. That's where that equation comes from. So it's nothing too crazy there. It's all just from angles. So I plug that in there, I get 5 sine of 30 degrees. I know you've never done sine of 30 degrees before in your lives, so hopefully you don't know that means a half. It's a half, which is 2.5. Okay, so that's my normal Mach number. Remember, we do everything in terms of normal Mach number. Everything. Oh, this also wanted to know what delta S is, like how much entropy is created by this wave. So we'll come back to that towards the end. A very hard equation. Now, since we have this, where we're going to go? We're going to go to the appendices. We're going to go to the appendices. We're going to pull out pretty much everything we need from there. So I'm going to jump over to the appendixes. Try again. Oh, there we go. And I want to go down to a Mach number of 2.5, which sadly does not exist in this table. Of course. Or it does. Yes, I don't have to do any math. Well, I have to do some math. I have to do less math, okay? I have to do less math. And so let's see here. We're going to need probably P2 over P1. We're going to need T2 over T1, P02 over P01, and P02 over P1, and the Mach 2. So pretty much everything except for the densities. We don't really need the densities for this problem. I think everything else, though, is probably going to be very helpful to us. Yeah. So let's use everything else. Okay, so here I am, 2.5. I'm going to go ahead and screenshot this so you have an easier time of seeing what information I'm pulling out. Screenshot. Capture the full page. And let's underline it. So this one right here, that's P2 over P1. Here is T2 over T1. This should be P02 over P01. This is P02 over P1, and this is M2. All of these are helpful. And all of these are needed for this problem. Just one last thing to remember is that the Mach number you get after the shock wave, that is not your total Mach number, that is the normal Mach number to that shock wave. So let's take all of that information that I just grabbed and bring it back here. Okay, bring it back here. Okay, let's see here. So I'm going to write it down, not in order. P02 over P1 is equal to 8.526, I believe. I gotta jump back and forth with that one because that one's not actually in the solution, but it makes it a lot simpler. There we go. Everything else, though, is pretty easy. So I have M normal 2 is equal to 0.513. I got that P02 over P01 is equal to 0.499. I have T2 over T1 is equal to 2.137. And let's see, last thing here is, yes, P2 over P1 is 7.125. There you go. And so that's all from Appendix B for a Mach number that equals 2.5. Okay, that's all coming from there. Now let's start using these values we pulled out to solve the rest of the problem, because this is enough. Like, we have enough just as it is to solve everything. Okay? Absolutely everything, which is gonna be great. Oh, wait, we'll have to do one other appendices thing for the total temperature, rats. We'll get to that at the end. So first off, let's do P2. So P2, the pressure after the shock wave, is going to be equal to P1 times P2 over P1. Pretty easy equations. You'll see these a lot. And so from that, I have that it's equal to 2.65 times 10 to the 4th pascals, all times that ratio, which is 7.125, which is a pressure, static pressure that is, after the shock wave of 1.89 times 10 to the 5th pascals. Okay, that's one done, not too terrible. Let's go to the temperature now. So T2 is equal to T1 times that ratio we got from the appendices, T2 over T1. So that's going to be equal to my temperature initially, which is 223.3 Kelvin, times the ratio, which was 2.137. Okay, we plug that in. What do we get? We get 477.19 Kelvin. So it's getting higher pressure, greater temperatures, which is what we should expect going across a shock wave. And let's do, we'll do total pressure now. So P02 is going to be equal to P1 times P02 over P1. As a note, we could have gone to the Appendix A to figure out what P01 over P1 was and got a very similar thing. You could have done P1 times P01 over P1 from Appendix A, and then P02 over P01 to finally finish it off. I just don't really understand why I would do that, because it's an extra step. I will have to still go to Appendix A for the total temperature because, you know, the shock tables don't give me that, but it does give me this nice little relationship. And so if you have it, use it. Just why make it hard on yourself? So it'll be equal to 2.65 times 10 to the 4th pascals. And P02 over P1 is 8.526, which should come out to be somewhere around 7 times 10 to the 6th pascals, which in other circles will be called just 7 megapascals. We're keeping it in pascals because that's what your book has it in. I'm trying to keep closer to that. Okay, so all of these are the pretty easy ones. However, if we want to finish this problem off, we still have a few things we want to get. And for T02, we don't have enough. Okay, we don't have any information on T02. Well, we know that it's equal to T01. We know that part because across the shock wave, your total temperature does not change because your total enthalpy is constant. But we still don't have a relationship here. However, using similar ideas to what we've seen in the past, I could probably say, well, that's probably going to be equal to T1 times T01 over T1. And just so you know, if you're ever trying to find the relationship between stagnation properties or total properties and static properties, then you always go to Appendix A. So this right here, that's going to be from Appendix A. That's backwards arrow. There you go. Appendix A. And for what Mach number? Same Mach number. Actually, sorry, not the same Mach number. I'm being slow down. This is going to be for Mach number equal to 5. Somebody tell me why it's Mach number equal to 5. Not 2.5 like it was for the normal Mach number. Yes. So the big thing here is that Appendix B is all about shock waves. Appendix A, there's no shock waves in Appendix A. Like, you can't have a shock wave and be isentropic. Like, that's the whole point. Shock waves are not isentropic. And so this is always talking about me, like you can imagine it that the isotropic flow properties tables, for any of these relations between stagnation pressure properties to static properties, it's as if saying, hey, what would have happened if I went from 0, not moving, to this Mach number? What would the relationship be if I did that isentropically? So that's the question here. It's always doing that relationship. So for a Mach number of 5, because that's the speed at which I'm moving before the shock wave, going all the way down here, this column right here is the correct one. Make sure I'm correct, yes. I can find that relationship between total temperature and temperature. So it would be 6. Oh, nice. That's always cool. Okay, so it'd be a value of 6. So with that in mind, I'm going to keep on going. Okay, so this is going to be equal to 223.3 times 6. Whoa, I like it. And that comes out to be 1,339.8. One little detail here, I did realize that I had a decimal place wrong on this one. That should have been 85.26, I believe, not 8.526. It's a much bigger ratio there. I think that should be correct so long as I did everything else right, which is always up for debate. Okay, so we have our total temperature right there. And let's keep going. Should be good. I believe it is. Yes. So last little thing to ask for was what is my change in entropy? And so for that one, we're using that equation. Delta S is from our TDS equations. We just integrated them. And we got that equal to negative the gas constant for air times the natural log of my change in total pressure. So I said change in total pressure, I meant ratio of total pressure. So big thing there is the more your total pressure drops, the less efficient you are, the more inefficiencies there are, and therefore the more entropy is being generated. So that's pretty easy to plug in. So I just have negative 287. That's joules per kilogram Kelvin. And then I do the natural log of the ratio, which is 0.499. What do I get? Well, the entropy generated is 199.51 joules per kilogram Kelvin. And we've got it. Looks good. Happy days. Okay, with that in mind, let's see here, make sure I'm not missing anything. I do want to check this guy right here, the P02, real quick before we move on, just to make sure I didn't have a wrong ratio there. So I'm going to jump back to the tables and check that. So Appendix B, Mach number of 2.5.
I think it is 8.526.
It is. You are correct, 8.526. That is, whoop, here's freeze on me a little bit. There we go. That is P02 over P1. So it should work, but the values are not coming out properly. Interestingly enough, they're different than if I had done it differently. So let's try it both ways, and I will figure this out later. Okay, so we're going to go down here and find out what P01 over P1 is. And that's for a Mach number of 5. Always good to check these things. Went too far. Didn't go far enough. There it is, Mach number 5. So it'll be 529.1. Okay, so let's try this out here. So I'm checking this guy right here to see if it comes out with the same answer. Because that number I just pulled it from the solution. I didn't actually type it in my calculator, so I'll check that too. So P02 is going to be equal to P1 times P01 over P1 times P02 over P01. It'd be equal to 2.65 times 10 to the 4th pascals. Multiply that by P01 over P1, which is 529.1, and then multiply that by 0.499. Okay, so that does 100% equal what I'm looking for. But interestingly enough, that value does not come out correct for this. P02 over P1 does not work for these two values do not agree. So this would be the way I would say to do it, since they are coming out with different values. 7 times 10 to the 6 pascals. Because this way is going to be more accurate, going from this and only doing the ratios of total pressures. Something I'll have to check and see if they've got it wrong in their appendices. Always fun to find errors. Okay, so we got one way I'm going to say is the bad way, and the other way is the good way. We've checked both now. That was fun. But yeah, this way right here, this is definitely the green way. Do this way, okay? There you go. Everything else should be fine. Okay, so we'll stop there and move on to the next problem.